both read and hear what I'm saying. I tend to speak more softly than I realize because I sound fine to myself, so that's the problem. Okay, it's annoying to everyone. Nothing we can do. Okay, so traditionally, the terminology that's used is call by name and call by value. And we will always use this terminology, and I don't pretend we're going to change it. But logically speaking, it's got nothing to do with call. Forget that. That's erroneous. And God knows where this comes from. I have no idea what this is. So it's just a noise that we make by name. Okay, I don't know what names are involved. I don't know what anyone's talking about. So that's some weird historical accident. But what I want to emphasize is the issue is the semantics of variables, and I began to broach on that last time. And so the thing that I was stressing is that the key issue is what do variables range over. And when you're in a situation where you have no possibility of any form of undefinedness, and I'm going to actually address a couple of them in this lecture, then the question doesn't really come up very much. But when you're in a programming language setting in which you have notions of undefinedness, then we care a lot, and there are different ways to understand what variables are based on that. So that's what I'm going to riff on, and then I'm going to develop some ideas, some I think rather fundamental ideas, keeping this in mind. So to start out, what I want to do is I want to generalize what I did last time. So last time, I introduced this little, admittedly artificial pedagogical device. It's a little language of circuits. So we had this little language for Boolean expressions. Okay, that's pretty simple. And the reason I did that is just because, for the hell of it. And I was particularly interested in the idea of a fixed point. Yeah, what? What, sorry? Larger, did you say? Larger?
Darker.
Darker I can't help. The pen is what it is. I don't know. If you give me another pen, if you give me another pen, I'm happy to use it, but I can't help that. Okay, so what I was particularly interested in is motivating, this might be a little better for 5 minutes, okay, is the idea of a fixed point combinator or a fixed point operation for creating kind of self-reference. So that's what I just introduced it because, it'd be a fun way to introduce it. So the next thing I want to do, and then we were analyzing what it meant to be a well-defined language, and we went through that. Okay, so what I want to do this time is I'm going to start out, first of all, with a little version of what is invariably called Plotkin's PCF, and that's what I want to do now because it helps me bring up some other issues that are at stake. Okay, so the key thing here, it can be described by the following idea: is that I add more types, okay, than just Boolean or just circuit, and in particular, I'm going to have the types 2, which are the Booleans, the type omega, which is the natural numbers, and I'm going to have a type of partial functions, okay, which I will tend to write like that. Okay, so that's the idea. So what we're going to do is this part is a very simple extension of what I did last time, just give a flavor. So if I write it down, what we're going to do now is we're going to have the notion of these are our types here, and then we're going to have corresponding forms of expressions, which I'll explain on this board. Okay, so the idea is that if we say we're doing the types are going to be 2 omega and partial functions, and then we're going to have expressions like we had before, so particular variables. I'll leave the 2 part as we had before with conditional, so let me just write it, it won't hurt. Okay, so I'll do it like this, and I'll have the if E1, E2 like we had before, and then I'm going to have a corresponding thing because it helps me to make some pedagogical points to introduce these usual 0 and successor, okay, and the analogous thing is if Z, and the difference is it binds a variable in the else clause, okay, and the variable would be bound to the predecessor. That's the idea. And then what else do I need? I need to populate the function type. So here finally we get to lambda, so we'll have some kind of notation. Usually you indicate the domain and then write this, so that's our lambda, and we have a notion of application E2. And then the thing that continues to stick out like a sore thumb, but I'll just throw it in here anyway, which which is the idea of a fixed point. Okay, so this guy is a bit of an orphan, and I will, by next lecture, get rid of its orphan status and have it be adopted by a proper type notion of typing. So we'll get to that. But for the moment, it's just like a bit of ad hocery. This goes with that type, this goes with that type, this goes with that type, and then this is some random thing. Okay, but that's where I am. That's what I'm going to do. And then we proceed as we did before. So the statics is generally going to have a judgment of the form e tau, and if you like to be explicit, then with respect to some assumptions about variables, so we write this. And this is, instead of just saying E is a circuit, we say it's an expression of type tau. Being a circuit means it's of type 2, and then I can write those rules down. I'm going to figure you know what to do here. Okay, so all right, I won't write that all out because it'll take a lot of time, and you can look at PFPL if you don't, and I can be happy to help in question time if you like. And we're going to have a dynamics. Oh, before I mention the dynamics, and I will say that this is going to be structural. I'm going to arrange this to be structural. Okay, that this will work out well. One thing that is, in other words, we're going to have all of the properties of variables we've had before, and in general, it means that variables range over expressions, which are going to be computations. We'll make that distinction more precise in a minute. So it's computations, or general expressions. And that's what's important here. Okay, so I'll just say that this is understood. I could take an opportunity here to mention one thing because it comes up. You might ask me the question, well, how could it ever be that I screw it up and things aren't structural? Well, here's I don't know if screw it up is the right word, but here's a common pattern that people adopt sometimes, which is like a typing for if, and they'll say this. They'll say, well, if E1 is tau, and they usually put all of the context in there, or we can just write it in local form and say if E1 is tau and E2 is tau, then assuming X is in 2, then if X, E1, E2 is tau. Okay, that pattern you'll see, people will write this. Because they're sort of saying, well, I want to say a certain map exists, and a map is given by substitution for free variables, so you write it like this. The problem is if you write your rule like this, it's not closed under substitution. Okay? And so you have to figure out what are you going to do. Okay? The reason being is what you're saying here is the only form of well-formed syntax is one in which this is literally a variable. Well, that's no good, because if I plug in for that variable like true, I'll have a malformed thing. So it doesn't make sense. So that's an example. So you can't do that. So what you usually do is, in order to ensure, if you wish to ensure that the structural properties hold, you just put up here that E is in 2, and then write that E, and now it holds for the general case, and the one we had before is derivable. So that's a reason, that's an example of a technical thing that can come up. So enough of that. So that's what I wanted to say here about the statics. The issue is about the dynamics, and I'm going to start out with a formulation that has quite a pleasant initial feel, but maybe I will suggest that it's not so pleasant after all. Okay, but let me try to do this. So we're going to give a dynamics, and it's going to be given in the form of a transition system. And so we'll have it like this. So this is using SOS. And you recall the reason for doing this is that if I have just an evaluation relation, there's sort of different kinds of situations in which there may not exist a value for a given expression. One is that it just keeps evaluating forever. The other is completely ill-defined. So we want to distinguish between, that was my motivation, like x.x, that does not have a value, but neither does, and now, I don't know, I'll write some random thing that I feel like writing, okay, just to be nonsense. Well, that doesn't have a value either, but I want to distinguish those because this is like a mess. This should be ruled out. This should be ruled out by the statics, whereas in the setup that I'm doing, the statics does not guarantee termination. If you do that, that's what I did in the very beginning of the lecture last time, then there's no reason, and we can just say everything has a value and everything's good. But as soon as you want to allow this to be statically well-formed, but that not, then you have to make a distinction. If you want to make a distinction, this is what you do. Okay, so this is how we're doing that. So that this will not make a transition, but this will to itself. And so it's kind of nice because this makes a transition and it's well formed. This does not make a transition, and we want to rule those out. So that's the reason it's done that way. Okay, so that's how you do it. So what is a dynamics going to look like? Well, how about if I say as before, but? Okay, in other words, I'm going to add, so all the stuff about 2 I'm going to leave alone. And then I just want to say what we do with the new stuff. Now, a lot of this will be predictable, but it's a device for me to be able to explain to you what's happening here. So we're going to say 0 is a value, like itself. And now I'll start out, and this is in the style of Plotkin's PCF, which says any successor is a value. So I can write over here, maybe exclamation point just to remind you, okay? So this corresponds to what is often called the lazy interpretation, or by name, or, well, there's various words, okay? So this is what I'm trying to express here. And then I can say, well, what happens with the elimination form? Well, you have to write these rules out. So we have if z is the new one. And remember, it binds a variable here. Oops, I'm sorry, that's what I'm writing is supposed to be below the line. So what I wanted to say was, if you're going to branch on a conditional, whether something is 0, you better figure out what it is. Okay, so you have to do that. So in other words, my point is, in this position, there's no options. There's no alternatives one could consider. In fact, if I want to do this, I could say, put this in brackets and mark it as, by value. Just to say, that way I can write 2 rules at once, in a sense, by a little convention here. Okay, so we can do that. Here I don't have any choices, so we just write that. And then you know what I'm going to do next, which is I'm going to say, well, if this actually is 0, then the transition is going to be E1. Maybe I should have called that E0. But anyway, and then if you have successor, now here's the critical thing. Provided successor of E is a value. That could have 2 different meanings depending on what you do over here. But I demand that it be a value. See, that's important. So in the by name interpretation, it's always a value. So you could say, why am I even bothering to do that? Well, because I want to make it work smoothly with adjusting little options. That's why. Okay, I do x.e2. And here what I do is I plug in E for x e2. Okay, and again, we have to be careful because if we're in the by name interpretation, it means an arbitrary computation which might be undefined. So variables can range over undefined things. Okay, that's a peculiarity. Okay, so that's how we would do that. That part is easy. As is the next thing. We do lambda. If we look at what a lambda is, let's say we specify its domain, then that's just going to be a value. And then we do the usual thing. And now, again, we're going to have an issue, which is things about evaluation order are going to come up here, and you know about this, I'm sure. And so in any case, if I'm going to apply something, I have to figure out what I'm going to apply. So I don't have any choices there. Then there's an issue about whether one decides that given that I have a value, what do I do? Well, as you know, the by value interpretation says, well, in that scenario, then I work on the argument. Okay, and then this makes a transition. And E2 prime. Okay, and then I need the famous beta rule, and I don't have space for it. So I don't know what I'm going to do here. I'll stick it up here. I hope it's not too terrible to do that. So then I will have the rule that says lambda, whatever the domain type is, it doesn't matter. There's some certain artificiality here. Okay, and then I'm going to go to E2 for x. Excuse me, what do I want to say here? E. Okay, and this is under the circumstance. Okay, this is the, and then you may want to demand that E2 be a value if you're doing by value. That's the way to set it up. So I'm doing this, I'm really giving you 2 dynamics. I'm giving you a by value and a by name dynamics according to how we exercise our options. Okay, so that's what we do here. So let's first of all look at the by name dynamics. The by name dynamics has a really good, so the message I sort of want to deliver is the following thing, is that The by name works well for negative types. They're so-called negative types, which in this case really means just the function types. But if I had product types, which I could put in with projections, products would also work well. Okay? By name, also known as lazy. The by value works well for the positive types, which by here what I mean is this will be 2 and omega. In general, it would be sums and things of this nature, inductive types, things of that nature, okay? And not vice versa. In other words, okay, if you want your negative types to work well, good. Then you can do things by name and your negative types will work well. And then if you want to be a good car salesman, you just call attention to the negative types and you forget all about the positive types and then you say, oh, look how beautiful it is. So an example of that is, in a by name setting, it makes sense for me to define the NOR, let's say, which has to be left strict, which is the one I was defining. It makes sense for me to define this to be, well, lambda, I can actually use a lambda. This is the part where people are seduced. So they say, okay, yeah, this is kind of cool. Take in a first argument, take in a second argument. Okay, and then what do you do? Well, you do the conditional branch that I mentioned before. So if x1 is true, the answer is going to be false, and otherwise it's going to be, I'll just say not of x2 if you forgive me, and we could write what not is, and it also would be a function. So the point is that this can be a function. There's a function exactly because the arguments are not evaluated on call. Because if we try to do this in by value, that doesn't make any sense. The whole short circuiting is completely out of the game. Like, we're going to be forced to evaluate the 2 argument positions here, which are represented by x1 and x2, and that's exactly what we didn't want to do. We want a short circuit here. So there's no possibility of defining it as a function. So in a by name, it seems like a very good thing to do. Okay, a lot of emphasis is placed on this, but I think the emphasis is misplaced. And I will explain 2 points about this. The real issue is that as things stand here, in one case the positives work out, in the other case the positives don't. Vice versa, in one case the negatives work out, in the other case the negatives don't. It's a wash. Neither is more mathematical than another. Neither is more better behaved than another. They're different. But there's a crucial additional point which I will mention. You can encode or even represent, I don't know what the right word is. If you're in a strict framework, you can actually reproduce all the behaviors you want in the by name framework and not the other way. Therefore, this is superior. That's my point, and I will get to that. Okay? Once you've screwed yourself by not specifying the evaluation order, you can't get it back. If you do, however, specify the evaluation order, then you can get a good cost analysis, you can do parallelism, and you can get back the relaxed evaluation order by a device I'll explain. It's a hands-down victory. There's like no question about it. So that's the thing I want to say. Let me say one remark about the that I mentioned last time. This is the kind of thing that looks nice. You know, this is a good thing. It looks cool. In some sense, in this setting, the if can be thought of as a function. I've seen people make a big deal about it. I think that's quite erroneous, really, because these things are implicit binders. So I'll explain that when I talk about sums. What's really going on here, the reason these 2 guys are not evaluated is not because, oh, some magic about call by name. No, that's not the idea. The idea is that these are both in the scopes of binders, and we don't evaluate open terms. I'll get back to that later. That's the real reason these are not evaluated. It's a complete mistake, okay, to explain it otherwise. However, it still is handy when the principal argument, and it can be handy like this, and that looks good. On the other hand, with by name, there are no Booleans. And there are no natural numbers. You cannot have them. I don't care what you do. There's no ruse you can make. You cannot have them. They don't exist. Why? because undefinedness plays the role of a value. I can plug in. If I have a variable, x, so what I want to show is I can do the following thing. Given x is in 2, you would say, well, if I have Booleans, the following pattern of reasoning should be correct. If x is in 2, then x converges, let's say, has a value. And I should be able to prove this by induction, you would say. If I have Booleans, I prove it by induction. Well, true converges, false converges, and therefore, for every x in 2, x converges. Wrong. Because I can plug in for the variable the divergent computation. It's undefined. You treat undefined as a value. Reasoning by cases is never valid for a Haskell program. The same thing applies with natural numbers. You say, oh, 0 converges, the successor converges, therefore every natural number converges. No, because what is called the natural number includes the divergent computation always, even if you make the successor strict. Don't tell me about strict annotations. I know all about it. Irrelevant. So the point is, so then I would ask you, so what's more mathematical? A language that like has no natural numbers? What? Okay, that's completely crazy, okay? You cannot make a firm distinction one way or the other. That's just completely erroneous. The only thing that happens is, yeah, the behavior of functions, the negative types, they work out more smoothly because, for example, it is the beta, which may have gotten erased up here, is universally valid regardless of what E2 is, even if it's divergent, okay? And then sometimes that's even sold as an idea of efficiency, and I'm going to argue that the exact opposite is true. So I'll get to that a little bit later. It has to do with complexity analysis and cost semantics. Mostly Jan is going to talk about that. I'm a little bit setting him up here. That's what I'm trying to do. Okay, good. So that's what happens over there. So to me, to have a programming language in which you cannot have bits, you cannot have lists, you cannot have trees, you cannot have natural numbers, you cannot have any inductive type is insane. This makes no sense to me, okay? And however, you might say, well, you know, maybe that's just the way the world is. It's not the way the world is. I can have it both ways. That's the critical idea, okay? So that's a point I wanted to make there about by name. So now let me look at what would happen with by value. What do we do here? So I pointed out to you last time, I didn't repeat the rule here, but I pointed out to you last time that if you wanted to look at the transition rule for a fix, we're going to have an issue because it's defined by unrolling. And this is fine for by name because variables range over computations that might be undefined things. Okay? However, what do we do for by value? How is this supposed to work? How are we supposed to get self-reference? Well, I'll tell you the trick. The idea is to make a modal distinction between values and computations and be careful about what we're doing. So here what I'm going to do is I'm going to develop a formulation. I'm going to reformulate. You see, it's traditional. And I have to say, if you look at my supplemental notes that I mentioned to you yesterday, you can look up what I would think is the right way to do it. When I originally wrote the book about 10 years ago, this section of the book about 10 years ago, I made the traditional mistake because I was trying to appeal to conventional wisdom. That's never a good idea. So usually people say, oh, you know, you can do it this way, you can do it that way. And I wrote it like this. You can just have various options and you can do whatever you want. That's not the right way to think about it. The reason is I have to bring out in the statics what is the semantics of variables? What do I mean by a map? And that comes prior to specifying what the dynamics is. That's why, so the call by, the issue has nothing to do with calling anything. And really the issue is how do I get the semantics of variables to work, okay? To express, so what I'm going to do to actually get the eager formulation to express the by value variables. And then that will allow us to go forward. Okay, that's the idea. All right, so that's what I want to do. And I'm going to use some ideas. There's quite a history of these things. The formulation I'm going to use is called lax logic. It's related to Paul Levy's call by push value, but it's not the same thing, but more or less, but it's in that thing. It's also Zeilberger's analysis of polarity. Okay, there are various ways to formulate what to say it. I'll just gesture at those words for you to look up to see what I'm doing. I'm going to synthesize something from that. Okay, so the question would be, I'm arguing that in order to specify, so with something like PCF, it's not really a matter of diddling the dynamics the way I suggested. It's really a matter of specifying the semantics of variables, and now I figure out how am I going to do this. So the way I do it, and then it pays dividends all day long. It's kind of fun how nicely this works out. So I'll show you this. So the key idea is this. Is a modality that distinguishes computations from values. There is a version of this which I call valuables. I will not bother about this at the minute. I'll gesture at it, what I mean by that in a minute. I'll just do it in the simplest possible way. The important thing is it's a modal distinction. That is, we have two modes of expression. The modes of expression are computation and values. And the way this is going to work out is we're going to have, as ever, we'll have some variables, which in this setting will always range over values, and that will be indicated by the fact that I use a colon. On the other hand, I have variables ranging over values, that's implicitly, and then I have computations, which I'll write M just to avoid getting confused. I'll use different letters, which is a kind of weak or lax typing that says, well, M would be of type tau if only it terminated. That's what this is going to say, okay? So when you smush these two things together, you're borrowing from kind of a math setting an idea that's not applicable in a programming language setting, which is to try to say, oh, I don't bother just making such distinctions. All expressions denote, but they don't all denote. Now, you can set up your programming language such that they always denote, and I alluded to that last time. Henry pointed out to me correctly that, yeah, I'm probably exaggerating the significance of, whether in practice you can do well with a completely total language. You probably can. I just wanted to give some sense of why there are limitations and what the arguments are on the other side. I'm leaving aside right now the possibility of everything being terminated. If you have that, then there's no really important distinction about by name and by value, except for cost and except for parallelism. So in the US, we care about complexity. We care that an algorithm is n log n as opposed to 2 to the n time. Okay, in Europe, you ignore all that. Okay, so I care about this. I'm an American. Okay, so a theory of computation must account for complexity. To me, it's insane to ignore this. Okay, so even in a total language, the distinction is going to matter because of cost. Okay, but anyway, for now, I'm in this partial setting, and so I'm going to emphasize the partiality. Okay, so that's good. All right, so we set it up with two modes. So these are the values, which have a so to speak strong typing. They literally are values, so they have that type full-throatedly. These are kind of maybe a little kind of equivocal about whether they have that type. That's the idea. So these are the computations. And this is kind of the weak thing, and this is strong. But in every case, the variables range only over values because they have a colon here. So in particular, I'm going to have a following structural property. So what we will have is, if I look now, if I just populate the syntax, it'll help give you some handholds. So what I'm going to do is I'm going to say, like, these are going to be values. Then there's going to be a question of what I do. So 0 will be a value. I have a choice here. It's not forced on me, but one thing I can do is say, successors of values are values. That's a possibility. I could also say in another way, okay, and just allow that to be a value regardless. That's entirely possible in this setting. That's a little bit of a hint of what I'm really going to do, okay, and why the one dominates the other. Okay, so you can write it like that. So you can those, and what else should I have? I think I should have lambda as values. Okay, and that's what I want to do syntactically. Okay, and then the computations. Now there's a question of syntax, okay? For emphasis, I sometimes will write return v, but typically people just say every value is a trivial computation, the computation that returns v. It's a finicky issue whether you want to make a syntactic distinction there or not. It's a question of making the inclusion explicit. That's all. So the important thing is that. What else do I have along here amongst computations? Well, I have to think about what are the apparatus I have in PCF. So let me look. So what will happen is you're allowed to do a conditional branch. Whoops, I'm sorry. That should say M1 and that should say M2, where this is a value. It's predetermined already what this is. I don't even allow anything else. So I'll see what I mean by that in a minute. So in particular, it could be a variable. That's the way this is going to work out. The same thing will happen with if z. This will be M1 and this will be x dot M2. Okay, so that's the way those work out. Let me look at what else I need here. And I'm going to have app, okay, and it'll be V1, V2. Written like that. Okay, that's the syntax. So let me look at the statics, because the statics is where the action is. So I have to explain the statics. When I explain the statics, I can then explain the structural properties that you want for this language. In other words, the ones I stated before, which are kind of motivated by logic, are not universal, must always hold for every language. No, it depends on what your dynamics is. Okay, so I'm going to explain how that works in this setting. Okay, so that's where I'm heading. That's my next thing going on. Okay, so now we set that up like that. I think I have everything. And I'm going to say something about fix. Will come up in a minute. Okay, I'm going to leave it alone for the time being. The reason is I obviously can't adopt the same fix. Because if I adopt the same fix, how am I going to evaluate it? Well, it appears that I have to unroll it. I've forgotten where I wrote that rule, but anyway, somewhere I wrote it down. And it's going to unroll and it's going to substitute a computation for a variable. No, we can't have that. But I'll explain a nice way to think about how that works in a moment. Okay, so we'll get back to that. So this is what we do. So then we have typing rules exactly the kind you expect. Variables are typed in a strong way, so they have the types that they have. They're strong. Okay, and we can say, now you'll say some very obvious things like true is 2 and false is 2. All right, so that's there. And I'll just intermix the weak and the strong. So I will say, let's put an if here. So I say if v is a value, well, it could be a variable. If it's closed, then it's going to be true or false because of typing considerations. We'll get to that. But if I do that, and then I do M1 and I do M2, then that weakly has the type tau if both M1 and M2 weakly have the type tau. As I say, a useful baseline intuition is either one of those branches might diverge, so I have a weak thing. I'm going to quickly account for other things, but let me just do this right there. A very similar thing applies when we talk about the numbers. So 0 is an omega, and then we say, well, if v is an omega, strongly, the successor of v is an omega, but the branching is going to have only a weak typing. Okay, so if we do if z, v e1 x dot e2, that's weakly of type tau. If v is an omega, e1 is weakly of type tau, and given that x is strongly a number, okay, then e2 is of type tau. Okay, so that's what we do there. And I'll move over here. Yeah. Not right now. I will get the moment, and I'll get the moment when we make the break. Okay. So this we have here, and then we have what to do. Application is the last thing I need to do. So I have a v is a function type, and v2. Oh, I didn't do the lambda. Well, I'm doing it in funny order. Tau 2. Then we will say that the application v1, v2 is tau weakly. Intuition being, you're going to call the function, and the body of the function is going to be a computation, which I will say right here. So if x is tau 1 and m, let's call it m2 for the sake of the notational symmetry, then I'll say that lambda tau 1 x m2 is a partial function from tau 1 to tau 2. I'm gonna riff on this in a minute, but I'll get back to that. I'll get back to that for right now. Okay, so that'll be good. So we do the statics here, and I'm omitting discussion of fix for the time being. I'll get back to that momentarily. Okay, so that's the statics we want. So what I want to do, and then the key structural properties. Okay, what is the substitution property? It'll be a kind of a lemma. And the substitution property is going to say, oh, I omitted something here, which I knew oh, no, it'll come in a minute. Okay, yep. So the lemma that I'm looking for is going to say the following thing. There's actually two forms of the lemma, okay? One is if I have this, and I have something strong of tau 2, and let's call it v prime, and I have the v as tau, then I can substitute v for x in v prime and get tau prime. And item 2 is if I have a computation, let's continue to call it m prime just for the sake of the notation to line up. And again, we have a value, then we can plug that in. That's the critical thing. And this is expressing call by value because it's telling you what the semantics of variables are. Okay? It's telling me the only thing I ever expect to be able to do is plug in a value for a variable. That's what's important here. Okay, so that's good, okay, as we've done so far. All right, so you can set this up, and then I can ask you to check as an exercise that even what I've written down so far, check that we have progress and preservation. Okay, so I'll let you do that. I'll leave that off to the side. So this should work. But I have better access. Can we resume? Is that okay? Yeah. Okay. Good. I think I can hear myself. I'm being projected, right? That can't but help. I'll do my best with the board. I'm sorry. It's difficult to do. Okay, I'll do my best. Okay, so now the thing that I wanted to do is to pick up from here. I guess I'm not sure which order I should do things, but let me explain over here I'm not quite done there yet, and that's the point I want to make. But let me just say, let's look at what is going to happen with respect to the dynamics. What does that look like? Apparently the blue is more readable. I don't know. I'll do whatever you want me to do. I'll try. Okay, so the key thing is it's computations that compute. So I can say a computation is done, or I can say it makes a step. That's the thing I'm going to do, and I can populate these rules in a minute. The values are given in such a way that there's nothing to say. The value is a value, and that's it. It's already been done. It's possible, as I alluded to earlier, to generalize the values to allow me to do trivial things like add two numbers or something, things that are total that we know are going to be there. That would be convenient, but my purpose in this lecture is not to maximize convenience for the programmer. That's another issue, okay? So I want to just kind of get the semantic skeleton of what's going on. That's my purpose. So we'll just say that we're going to execute like this, and I'll populate that in a minute. Okay, so the idea is this is how we compute. We compute by, making transitions or simplifications on computations, things that I call computations. Now, the thing is that, first of all, I have what is the mode distinction between two forms of expression, I guess is a word to use. Two forms of expression, the value expressions and the computation expressions, I make that. And these things are linked by virtue of extend the type structure in the following way. We introduce a modality, which is the modal modality, okay? This is the modality, which is the computation modality. So what is going to happen here is the following thing. We have to decide, I wrote E here, that was a mistake. I should have written M, okay? I deliberately changed the syntax, and then I keep making mistakes with it, I'm sorry. So we read it like that. And then the issue is that we have values of the computation type, which are encapsulated computations, okay? So in other words, this thing is going to be, it's a form of a value. And if you don't mind me erasing so that I can work in place, the linking, the other part, right, I knew there were other parts of the statics I forgot to write down. I'm sorry, I got discombobulated there for a minute, so I did need to do some other things. But let me just say this here. So we say if M is weakly of type tau, then comp of M is strongly a tau comp. Okay, so that's what we can do. That's what we can do there, so that's a value. What I didn't do, because I got myself discombobulated. What I didn't do is I forgot to write down the statics for the computations, so I could also do that. So I might as well do that as I come upon it here. So let's look here. Okay, so what we want to do is this tau comp. Okay, so we have M as a computation, we can encapsulate it. So this is a type, and it has an introductory form, which is strict, and it has an eliminatory form, which is a computation. And the eliminatory form is a bind. And the idea is the following. This is important. It takes a value, which is of type tau comp, and for x in tau, let's call that tau 1 to this. I think this will make everything work out nicely. M2 is weakly of type tau 2. Then we do the bind v1 x dot m2 is weakly of type tau 2. And so I need another piece of syntax on here, and that other piece of syntax is exactly, I'll scroll over here, and that other piece of syntax is bind with v x dot m1, and I've now given you the statics for that guy. So while I'm remembering to do what I ought to have done already, we have the convention that if v is of type tau, well, one version of it is I specifically say return v to be weakly of type tau. Anything that's strongly of type tau is weakly of type tau. I could just omit the red if you want. Okay, that's a detail. Okay, so we can do that. And then we can write other rules just so that we can get a sense of what we're doing. So let me write the rule for application. So for example, if V1 is strongly, oh, I did that. No, I did it en passant. I'm sorry, I didn't. Okay, well, I'm discombobulated now, so I wrote this here. Okay, so the application is weak. Why? Because the body is a computation. So if I'm going to apply it, and I'm going to have an expectable sort of evaluation, so I could write over here on the dynamics, you could very well imagine I'm going to do this. A particular form of computation will be the value turns out to be a lambda. Let's call it E2 here. And this will be a value because that's what it has to be. Then it will take the transition to V2 for x E2. Okay, so that would be one of the transitions. So, and that should have said M, pardon me. Maybe I ought not have adopted that convention, but anyway. Okay, so that's what I had in mind here. Okay, so this is a kind of transition between computations. Now the critical thing is, what is the dynamics of the bind? The thing that might, at first glance, if you're not familiar with this kind of thing, the thing that might seem strange is that I'm binding a value. Like, what? What am I doing here? Wait. Okay, so the point is it's a value of computation type. And so how do we specify the dynamics of that? In order to make room for myself, I'm going to erase this. Okay, that one you probably could have guessed in any case. So the question is going to be this. So if I look at ret v, that's going to be done. Okay, that's a terminating computation. I return 7, or I return true. Okay, I'm completely done. Now we have the following kind of scenario, and it gets a little bit, oh, it's written like this. So what I do is I say this. This has to be a value, and I'm only going to worry about the well-typed values. And so what I have in mind is when I prove progress and preservation, I'm going to have to characterize the closed values of a type. I'm going to know that the closed values of a computation type are computations. I have to prove all of this, but this is one of those things I'm going to skate over. It's in the book. Okay, so you can do this. All right, so we have a computation which is encapsulated like that. I'll call it M1, and I'll call this guy X M2. And the question is, how does that evaluate? Well, the trick of it is you go underneath that computation, and you evaluate here, and then you reconstruct the scenario with the updated computation. If you like to think of it this way, this corresponds to sort of what you do with call by need, except I'm not trying to do any kind of sharing or anything like this because I don't want it here. Okay, but there's a flavor of this. Okay, so I look underneath and I make a simplification step and I do it here. And then how do I know when I'm done? Well, if I manage to get the computation to a return, which is a final one, if I manage to get it to a return, okay, then that's good. Then what I do is I plug in the value v for x, and I do that in M2. And then we're good. Okay? The other kind of dynamics, as I mentioned, I gave you the beta one. You could guess for yourself, wherever they might be, how you would write out the computation statics for if and if the, and you'll do the right thing, and you'll know what to do. Okay, so the critical thing is really this. Okay, this is what's going on. So what is going on here? Let's understand what's happening. So what I'm doing is by demanding that the principal arguments be values, I'm putting back pressure on the type system that you previously evaluate those so that you can even write the application. Okay? So I'm forcing you to sequentialize by using the bind construct that's going on here, which is the uniform computation modality. Okay, so that's the critical idea. It leads to programs that look really several times. I'm not trying to be convenient. I'm trying to show you what's going on. So we're trying to get the skeleton here. So I don't deny the inconvenience. That can be handled by other means. That's not a problem. Okay, but I want to show what's happening here. Okay, so all the action happens in the computation. So now there's two things that I want to remark on, and they have some relevance for what I want to say, what else I want to do with this guy. Okay? So let me do this. So now the first thing I want to do is this, is one way to consider this idea of partial functions now is what you can see is, I haven't told you I'm going to have to say in one breath, I'm going to have to say sort of two things, but that are interdependent. So I'll cut the dependency arbitrarily here and I'll say the following thing. So the idea is this. If I take tau1, or the reason it's called that is that with a partial function, it means when applied it's a computation. And it's the computations that might diverge. Okay, yes, at this moment I haven't showed you how to do that. Bear with me, I will, okay? That's the circular dependency I have to cut somehow. So when applied, it's a computation. So there's an old idea that goes back probably to Moji, I think, in the late 80s, someone like that, is to reformulate this in the following way. Well, actually, it's a total function that returns a computation. And that expresses, when it's applied, I get back a computation. Okay? So in other words, we can say that this is notation for that. Okay? That's the thing we can do. That's an interesting idea for several reasons. One of which is it gets rid of the artificiality of the partial function. It's explaining what I mean by partiality by pushing it over here. More importantly, what it's doing for you is it's saying something about the type of the result being something that is a computation. I'm making a static distinction between things that might diverge and things that don't. And what is good about that is, I can use this in other ways. I can also talk about functions that take their arguments in unevaluated. I could talk about functions. It could be tau1 is actually a comp type. I don't care. Oh, and this would be a by name function call. Because it's taking an unevaluated computation as argument, and you evaluate it according to whether you look at it. Boom. So the point is, in this way, you can account for the behavior that we had before. The same would happen if we have something like an eager or lazy successor. So I'll write, I don't know, LSUC or something, would end up being an omega comp if it wants to be lazy, and will give me back an omega. This will be a total function that gives me back an omega. So this is a way of writing it. Okay, the partial function stands for that. So I take total function as a primitive notion, and this just returns a number out of a comp, as opposed to successor, which takes a number to a number. So the point is then you can just account for everything in this setting because I use type system to control the order of evaluation myself, and if I want to relax it, I can do it by replicating a suspended computation. I can replicate it wherever I want. Now I have no idea what's going on, but at least I told you I have no idea what's going on. Okay, so that's the important thing. I can recover all of the behavior, but I'm not screwed because we can now say, notice, we can prove this. A closed value, let's say, a closed value of type, let's say, 2 is a Boolean only, and omega is actually a numeral. It doesn't have any embedded computations. It's not like hiding a divergence. It's like completely well-defined numeral. In particular, then, we recover mathematical induction because for all x and 2 means for all values. Therefore, I can reason by cases. I can reason by mathematical induction. I have inductive types. I have my trees. I have my lists. I have my numbers. I have my Booleans. And there's no issue. Okay, so this is the important point. And it all arises from what is the semantics of variables. That's the critical idea. So what I've done is I've given you a formulation that tells you how to make the semantics of variables explicit. Now, there are other reasons for doing this which are wicked cool. But before I do that, I want to explain how I'm going to deal with fixed points. So how do we deal with self-reference? I deferred this, okay, I had to do this. So how do I deal with self-reference? Well, our original idea is once we kind of got the intuition that there are values and there are computations, it's the things that are self-referential that qualify as computation. That's a way of thinking about this. So the idea is the following thing, is what I do is I make self-referential computations. The way to do this is the following. We have comp tau x dot e. That's the important thing. This is a value, okay, that we do here. And this is my self-reference. Yes? And it ranges over a value, over values, because that's the nature of it. And the value in question is the encapsulated computation. So the idea would be, if I knew, so when I do an evaluation of a bind like that, I forgot what I wrote down. Let me make sure I'm on the same page here. Yes, I just do this. Yeah. So one way to formulate this. I'm just checking what I did. So one way to formulate this is you revise what I did over there, and you say, well, if I have a self-referential computation, and that's what I'm trying to do. Excuse me. That would be. I keep doing that. I apologize. It's my own fault. Okay, so we do it like that, and this would be, let's call that y, okay? God, my notation is terrible. Y prime or something like this. So what I want to do is to say, well, I have to unroll it. Okay, so I'm going to do some computation, and the idea is that, oh, God, I have to figure out what that is. I'm writing the rule upside down. What I want to do is do the unrolling, and what I want to say is if we take plug comp tau x dot m, which is a value, plug that in for x and do it on m, and then we want to make an m prime, and then we have to figure out what to do next. Okay? So we've unrolled it. So the unrolling has happened, and so we can put back here essentially a non-self-referential m prime. I think this should work. Oh, God, I shouldn't have called it m prime. I'm sorry about that. Let's call this x2, m2, and then I'll get that out of the way. Written like that. Okay? So the point is that you unroll when you inspect it. Okay? So that's the idea. So as an exercise, you can write for yourself, write out, for example, our RS latch in this notation using computation modality. Okay, that's a very useful thing to do. Okay, and work that out and make sure that everything is working. My argument is it'll be a little bit more clumsy to write down, but as I say, those issues can be managed. But the key thing is to understand like what is happening here, like what are we doing? Okay, so in this way now I've managed to account for the idea of a different way. So what I want to say is that the so-called call by value, call by name, I know we're always going to say that, but the call by value, call by name distinction is really to do with specifying the semantics of variables, which is to do with specifying the consequence relation I'm presenting to you. And the consequence relation has some properties that are not exactly the same as the structural properties I wrote before. They're related to that, but I'm making explicit that the only thing I demand is requirement. The only thing I require is that you can plug in values for variables and not arbitrary computations. So it's a different language. It's a completely different world. But the nice thing is, I'm not going to substantiate this any further. One can do an elaborate story to really nail all this down. By using tricks like this, just programming methods like this, I can have everything I used to have, and I have a lot more. In particular, I'm not crippled at the outset by being unable to express Booleans, unable to express natural numbers, unable to express trees. That's a bad idea. I don't want that. But 10% of the time I want to do some kind of delayed evaluation. That's true. I do. And what this is doing for you is saying, yeah, there's a matter of type. I'm doing that. So that's how that's going to work. Okay? So that's the setup. Then you have your cake and you can eat it too. Everything is great. Okay? So that's the setup that I had in mind there. So this is the sort of lax logic setup where we have this, and we can. I think that's just the way in which you present the different consequence relation, which has different structural properties. Okay, that's the critical thing. So you see, there's an interplay here. There are ideas that arise from logic without doubt. Okay, but you see, when we deal with, for example, partiality, or what I'm going to do next, which things that arise in real programming languages, well, then we have to adjust what those mean, because it depends what the dynamics is. It depends on what we're doing. We have to figure out what the right thing to say is. It's not always the thing that I said in the first case. It would be if I didn't have any of these phenomena. But the next phenomenon I want to deal with is exceptions, or some analog of, you could say, runtime error, although I dislike the idea of casting exceptions as errors. They're just a control flow mechanism that's goddamn useful. Okay, very useful. There's a lot of software methodology out there that denigrates exceptions, and I think they're completely mistaken. And I'll explain to you, I think in my last lecture, I'm going to explain to you the issues of confidentiality and integrity that arise with exceptions. And if you understand that properly, you will no longer want to denigrate them. Okay, so that's foreshadowing what's going on. I haven't actually listened to Andrew Myers' lectures, but presumably he's talking about such things. Is he? Yeah, okay. So the thing I'll say at the end will have some bearing on those things. So I'll get back to that. Okay, so now I want to present one of my favorite ideas. It's just such an elegant thing, I feel, is the idea due to Benton and Kennedy, which is about how to deal with exceptions in a very clean way in this framework. You may realize, or you may not, I don't know, that exceptions in by name languages are a mess. It's a complete train wreck. The usual formulation of it is, you plant these little landmines through your data structures, and then God knows when you step on a landmine, and kaboom, and some exception goes off, and actually the thing happened, God knows when, 6 years ago, and it's been sitting around in this list, and then you finally got to the 11th element of the list, and then because it's the 11th element, suddenly an exception goes off, and good luck figuring out what's going on. It doesn't make any sense. Because the idea of exceptions is to manage control flow. It's a convenient way to manage control flow. Okay, so here's the nice idea of Benton and Kennedy, which I like. This is Benton and Kennedy, which I like, which fits in very well here. What we do is we allow for two forms of termination. In a bind. So I mentioned I'm motivated here. In fact, it happens to be still on the board. I'm motivated that, I can say that in encapsulated computation, the idea of it is to manage when divergence can happen. Divergence is just one form of termination, or non-termination, actually, but one form. Divergence can happen. Divergence is one termination phenomenon that I want to deal with. Another one I want to deal with is a place where you explicitly decline to converge. And the reason you explicitly decline to converge is because somebody else is going to take care of that issue. Okay, so that's the whole idea. So what do we do here? What we want to do is we want to generalize bind in the following manner. This is what we call the ordinary return. So this is the bind. If I close parens, then that's the construct I've already been telling you about. But I'm not going to close paren yet. What I'm going to do is I'm going to have another thing. How about if I call that x1, x2, m2? And this is going to be the exceptional return. This is a really neat idea. And what goes along with this is you'll remember, what is an ordinary return? Return of v is the ordinary return. And what is the exceptional return? I'll call it raise of v. So this is ordinary return, and this is exceptional return. Now there's an issue. What sorts of values should I associate with exceptions? Oh, this is another mess in call by name. In order to do this properly, as I'll explain later, you need a notion of effect in order to generate new exceptions. There's no getting around it. if you don't have any control or evaluation order, you cannot do this. So the only way to do it is you, shall I say, fake it, okay? And because the only thing you can do, it can't be done in a call by name setting in the proper way. I'll get back to that later. So the question is, what are these values? For the time being, I'm going to say there's some designated type called tau x, and I'm not going to tell you what it is. Because right now I'm interested in the control flow aspect of this. And then I'm going to do a second control flow aspect of this. Okay, so we'll get to that. Okay, so what is it that I have in mind? So what I'm going to do Ben and Kenny's idea is so natural that after the fact you think, like, how do we not think of that? It's like obviously the right thing. But anyway, that's a sign of a good idea. You think, oh, it could have been otherwise? Well, unfortunately, but okay, but this seems like the right thing to do. I think kudos to them. Okay, so the idea then is this: so that we have new forms of computation. We have the one we had before, return of a value. We now have, I'll use the term raise. Some people use throw or whatever. I don't care. Okay, we can do that. So we can write raise of v, which I did before, and then we have the bind with the two returns. So I'm repeating myself here, but all right, x2, m2. So those are my forms of computation. Okay, and so the point is that this combines, this is sort of, so to say, handles both forms of return. And now, the rest of it, from here, once you have this idea, it's kind of a dawdle. So I did the ret of v. So what would raise of v be? What would be the, well, this is going to be a weak thing, because the whole point of it is it's declining to return. So it's only weakly of whatever bloody type you feel like, because it actually isn't going to return. And this has to be a tau xn. The choice of tau xn is very critical and important, but I'll defer discussion of that later. Okay, so it matters what that guy is, because exception values are shared secrets between the raiser and the handler. That's the idea. Issues of security, so-called, secrecy, privacy, confidentiality, whatever word you want to use, are central to understanding exceptions, I claim. Okay, so I'll explain that in a minute. Okay, I know another lecture. Okay, so we can go here. So we have raise, and then let's see. What else should I do? I can give you this rule is the statics is going to look the same. Really, it just has one more clause. So that'll be weakly of some type tau, and now you know what I'm going to do. That has to be strongly a tau xn. That has to be a value of that. Given x1 being let's see, I'm sorry, I made a mistake. That's not what I meant to say, pardon me. What I meant to say was this is a tau comp. Oh, hell, all right, let's call this guy prime. I hope I don't get in trouble. Okay, so this is a tau comp. Then, okay, this is strongly a tau. That is, if I really do run it and it does run to completion and I plug in a value, it will be of type tau, and then I will check that M1 is a good computation. And now for the so-called handler, okay, then this is where the tau xn come in. I made a mistake. Okay, so I do that, and then I say M2 also has to weakly have tau prime, in which case the whole thing has type tau prime. And then cutting to the chase, if I just look at the dynamics, besides return, if you do a raise v, if you have an encapsulated computation that raises v, okay, and you have x1, m1, and you have x2, m2, then where do you go with that? Well, now what you do is you go, obviously, to the handler, and you plug it in here. The other parts are the same as I gave you before. That's the trick. So this is the entire idea. So what are you supposed to think? The way to think about this, why is this a natural thing to do? Because really the result type is implicitly a sum. It's either tau plus tau xn. Either you return with a value of type tau, or you raise an exception which is returning with a value of type tau xn, and then the handler is just dispatching which it is. Done. That's why this is, quotes, the right thing to do. Okay, this is the right thing to do. And now it fits in completely smoothly, and that's what I have to say about exceptions. Okay? So this is another phenomenon about termination behavior. Later, I'll talk about tau exon, because one has to know about that. Okay? Okay, so good. So that's what I want to say about that. Now I want to say another thing pertaining to by value. So one of the wins about doing by value is you can encode the by name thing. Okay, it gives you greater expressive power. Second thing is I get a well-behaved notion of exception. I can make exceptions and I can handle them, and I know what I'm doing. I don't have exception landmines. Or if I do, I at least have to stipulate in the type that I'm storing unevaluated computations, and then you get what you deserve. Okay? It's not forced on you. It's not like, oh, implicitly, blah, 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 I have no choice. No, I don't say, oh, your NAT list is not really a NAT list. It's really a NAT computation list computation. Okay? No, I say, you choose what type you want. You know what you're doing. I don't want it to be forced. I'm making the distinction, then I can relax it. That's the remark I made yesterday about the affordances and strictures of a language, how they interact. The reason to do it. Now here's another benefit. Parallelism. Falls out very naturally. And this is a nice thing. So I want to say a little bit about parallelism. I could do quite a whole lecture at least on parallelism. I'll just say something. I have to make one or two preliminary remarks, and then I have to show you how it emerges in this setting. Where I'm heading is this, is that I'm going to change the modality. I'm going to use a different modality, because you might worry about the following thing. Okay, so I want to say something that at first is just a terminological issue. So the terminological issue is this. Let us please use parallelism as to mean it's entirely a matter of efficiency and not correctness. So in this respect, I'm dealing with a deterministic evaluation that has the exact same behavior, whether I do things, quotes, in parallel or not. The behavior is never in question, but the efficiency is. That's what it means to be on the left side of the pond, okay? So the efficiency matters. So that's what we want to do here. So we want to do this. And the key thing is that we want to be work efficient. And now this is going to seem like a dead obvious thing, but okay? So what I mean is to be work efficient. If you're exploiting parallelism, you must not, if you want to be doing it for any worthwhile reason to make things run faster, it should not be the case that you're doing more work just for the sake of being parallel. That seems like a dead obvious thing, okay, when crystallized in that form, but it ain't like that. Now we get back to the by name and by value distinction. With by value, I know exactly which pieces of work I have to do. Therefore, when I parallelize them, I'm going to be work efficient, because I'm just going to say, do these two things, which must be done in parallel. If I have no control over the evaluation order, I cannot do that without risking being work inefficient. Parallelism is incompatible with by name. Okay, that's the critical point here. Okay, so how do we do this? So if you take the framework that I set up here with lax logic, the thing that is like would worry, the sort of lax type system for call by value, the lax modality, seems, and I'll write seems, to impose sequentiality like all over the place. Why? Because, for example, I write app v1, v2. I said it puts back pressure on the programmer to previously figure out what the value, what v1 is by some encapsulated computation. Previously figure out what the value of this is, and I have to do them in some order. So it seems like anti-parallel. It's true as it stands. But let's not be so by this formulation of call by value. I can do this in a way. So here's the idea I want to make. The essence of parallelism is sequentiality. And the idea is the following. When things really and truly do depend on one another, if this computation depends on the result of that one, there is no opportunity for parallelism. They have to be sequentialized. It's just a matter of the semantics of the situation. But if they don't, let freedom reign. Do whatever you want, evaluate them in any order. So the intuition is this. When you get parallelism, it's going to look like this. It's a sort of fork join. So the idea is that, yes, this computation is waiting for the outcomes of all of these three computations. You have to sequentialize them. But horizontally, you can do whatever you want in parallel. That's the idea. So what I want to be able to do is express the essential dependencies and not force inessential dependencies. In many cases, there's no essential dependency between V1 and V2. I can do those simultaneously. So how do I express that in this setting? Well, let's not get too exercised about which modality. And what I'm going to do is I'm going to say, look, this computation modality is the unary case of something more general. Okay? So what I'm going to do is this. I'm going to generalize tau comp, which is a single encapsulated computation. I'm going to generalize that into what I write tau 1 ampersand tau n. I chose that notation to kind of get it out of the way of other things that you might think. Okay, so I wrote it like that. I'll write it infix. In fact, at the board, I'm going to do n equals 2. But really, there are two additional generalizations. One is any number, and the other is not even statically determined. I can do it dynamically determined. I'm not going to lecture about that, but you can look in the supplementary notes. It's written out. So this is the idea. This represents n unevaluated computations. Not one. And then I generalize the bind to a par bind in the following way. Okay? So what I do, it's best if I do this. So first let me do that. So I generalize that. And then I add a certain type, which is a strict tuple. And I'll write it like this. At the board, I'm going to do n equals 2, but it's an n-ary tuple. So this is an n-ary tuple of values. The elim form for this type becomes the intro form for that type, and I'll show you how that goes. They're simultaneous. And that's how we express the fork joins. I'll show you that. I don't want to obscure that, but that can't scroll, so let me go over here. So here's what I want to do to you. All right, so my types tau become, okay, things I had before, and then for the board's sake, I'll just do this. I'm going to add those two guys, just two. Okay. What are our values? Well, the things I had before, but now I'm going to allow you to form. I'll write it as E1 and E2. You could write it parallel. I don't know what the right notation is, but anyway, I kind of like this sort of functorial style notation, so I'll do it like that. Okay, so I'll write it like that. So that will be a value of this type, as it will turn out. And then I will also have, again, this kind of functorial notation. Oops. I'm sorry, I keep making the same mistake. It's my fault. Okay, this and this. Okay, that's the thing I have in mind. The point is these are not evaluated, and by God, the last thing I want is any sort of memoization. No, that's not the right idea. So I don't do anything like that. So what I'm going to do here, the memoization is a hack to make up for the fact that you can't control what the hell is going on. That's the issue. But anyway, let's leave that. So we can write it like this. And then what do we have for our forms of computation? Well, I'm going to generalize the bind to a par bind. And when I show you the statics, you'll know exactly what's going on. So I'm going to have V. Let me leave the exceptions out of this. It's no problem. I can just put the exceptions on Brent and Kennedy exactly the same way. Beautiful. The exceptions interact beautifully with the parallelism. You have to be a little careful in a certain way. I don't want to spend time on that right now. So let me just neglect that, but I'll write it like this. Or we can do it with exceptions. That's not a problem. Okay, that's a kind of a nice thing. Parallelism exceptions live together beautifully. Okay? All right, so we're going to have a par bind, but what is the statics? And that's the critical idea. And the idea is that if you give me a value of tau, let's just do the 2 case, then I'm going to turn it into a value of the eager product case, written like that, and get a computation which computes a tau. And then the par bind is going to take V and x dot m, and that's going to be a tau. So what is it that's going on here? What is going to happen when I explain the dynamics? What is going to happen is of two unevaluated computations. It's going to evaluate them both simultaneously. when they achieve a value, will form the ether tuple of their values and pass that to the continuation. That's exactly what I'm trying. And it arises out of typing consideration. Okay, a very nice thing. Okay, so the lim form for here becomes the intro form for that. That's the important thing. If there's a lim form for this guy, what does it do? It splits the pair. Okay, so I have a split of v x1, x2 dot m is a tau if v is strictly an eager thing, and with x1 tau 1 and x2 tau 2, I get that m is weakly tau, and this is weakly tau, so it's a split. The interesting part. So probably this guy is going to split that pair, obviously, but I'm going to arrange it so that it a priori creates this thing. Okay, so that's what we do. Okay, so what does the dynamics look like? So one of my points is this. Well, I'll come back to I have a meta point about this, but let me first write down what the thing is, and then I'll tell you what my meta point is. Because I have a backstory about this. Okay, so I'll get back to that. So what is it that I want to do? So what I want to do now, the critical rule is going to look like this. Oops, I'm going to do a parbind now. And by the way, when I do the n-ary case, I think it's obvious to you, the tau comp is just the unary case of the ampersand. Okay, it's a little hard to write unary infix ampersand, doesn't make sense, but you know what I mean. So it's a unary case of that. Okay, so what does a parbind do? Well, the issue is, well, I won't have comp here, right? What I will have is M1, let's just do the binary, M1, M2. Oh, I need to leave room for what I need to write above the line. So let's do this. Okay, so parbind. You have M1 and M2, X1, X2, M, which is the form of that. And we could do exceptions, but we won't. How do we make progress here? Well, that's exactly what you might guess now that everything I've said. You make progress on both of them. And you work them in parallel. And then what do? You get back to this guy. And this becomes M1 prime, M2 prime, X1, X2. The continuation is still waiting. The continuation is the join point. I've generalized the idea of continuation to join point. Okay, do you see what I'm saying? Okay, so that's what we do there. Then we say, well, if it happens that these are both done, let me put the red in to be emphatic. These are both done. They're returning V1 and V2 respectively. Now I can pass to the join point. If I have exceptions in, this could be arrays, that could be array, and that could be arrays, they could both be arrays, and you impose left to right order because that's the algorithm for, you just say exceptions arrays left to right. That's what we have to do. Okay, so, but we'll stick with that. So we have these two things, and then we have that guy. Okay, and what do? We plug in V1, V2, V1, V2 in mem. Ta-da. There we are. And now there's only one. Do you see what's going on? So what's happening is, in every round, these guys run simultaneously. Okay, these are parallel. Okay, so that's that's the basic specification. There's only one little mistake in here, which is it's important, but it's a bit of a finicky thing. Oh yeah, what happens if M1 reaches a value before M2 does, or vice versa? Okay, oh right, I have to do that. Okay, so now I have to put in some other rules. These are a little irritating. So I have to be able to say something like this. Let's say the first one has finished, but the second one hasn't, M2. That one is finished. And then I have X1, X2 dot M. Well, then I have to have a rule that says, well, we'll work on this guy. Okay, and leave this guy alone. And this will be M2 prime, etc. If M2 steps to M2 prime. And then plus the other way. And then we've covered all the four cases. So that's a little tricky thing. Make sure you get that right. Do you see what I'm saying? They both don't necessarily terminate at the same time, so you have to allow one guy to catch up to the other guy. When you put in exceptions, a similar thing happens. So it's a good exercise to you to figure out how to put in exceptions. Okay, so now we've done this, and now we have parallel computing in this setting. Yes?
Is there an issue if we substitute the V1 for X1 directly?
Could someone relay the question?
If we substitute V1 for X1 while waiting for the second computation to terminate.
Are you able to hear that?
Is there an issue if we substitute V1 for X1 while waiting for the computation to terminate?
Okay, what did I, oh, you say, you're asking me, could I reduce it to like, yeah, you could also do that, I suppose. If I understood you correctly, you're saying, why not just reduce this to get rid of the red V1, plug it in, and then carry, well, yes, you could do that as well. It's just when you get exceptions, you're not going to want to do that. Okay, because you have to keep track of the leftmost one, which is the leftmost one. Only then do you know which one to propagate. So it's kind of better to do this, but I understand your point now, sorry. Entirely valid point given what I've written at the board. Good. But I have other like things I want to do, so that's why. Okay, but that would be fine, yep. The person was just asking, just if one finishes early, treat it as some kind of partial thing where you partially completed the let and then continue the rest. That's what I'm doing anyway, yep. So yes, you can do that, but for the fact of exception. So we'll leave that alone. Okay, so then what this gives us is now the ability to express parallelism, and we're able to express sort of parallel programs, and we're able to evaluate their costs. Let me just check here. Yes, and you can check again here that you get type safety. It's going to hold for all the same reasons. Okay, type safety continues to hold. You can say, continues to hold. We really have to say you have to do this thing. It's a modest generalization. It doesn't compromise the type integrity of the language. Okay, so what have I said here, like at a high level? I should write programs for you. We can do that offline, or you can consult a book. I'm in this position with only 4 lectures. As I've mentioned, I have to rely on you to do back reading. And I'm happy to help you out when we go to a session. So what we have is we have a framework for doing things like parallelism exceptions, which fit naturally in the eager framework. And by virtue of having a type of computations, I can simulate all the laziness you want. Boom. This is the answer. There is no better way to do things than my knowledge. This is the right thing. Second other point. There's a big, kind of terminological emphasis on something called a monad, of which the things that are called monads are not. Because a monad is an algebraic structure in a category, and these things are completely not applicable. But what is happening here is, setting that aside, you could say that the unary version, the tau comp, well, it resembles some kind of monad. There's a big mania about the monad, but actually, let's not make a big deal about this. That's like one sort of typing structure that's handy in certain circumstances. But here, what I'm arguing for you is that I don't want tau comp because it forces me to sequentialize everything. What I want is tau 1 and tau 2, or an n-ary version of that, or a dynamically wide version of that. And if you look in the supplemental notes, that's all spelled out, so you can have a look there and background. That's the right idea. The emphasis on monads is crazy. It's completely crazy. Okay, it's like, why are you obsessing on that one thing? There's a million abstract types out there that are useful. So if you commit yourself to that, you're screwed on parallelism, forget it. Okay, so it's out of the game. So what I've done is weakened that, or strengthened it, I don't know, weakened it, I guess, to allow a more general notion of having multiple suspended computations, and then I get parallelism out for free. Now, the thing I want to close with that I'm not doing in my lectures is to define what I mean by parallelism. This, informally, you can feel it at the board. Things are happening simultaneously. But really, I started out by telling you that parallelism is a matter of cost. So the other side of this story is I have to do a kind of cost analysis, a way of assigning a time complexity, in this case, to programs that accounts for the distinction between sequential and parallel evaluation. So Jan's going to talk about cost semantics, so I decided I'm not going to go there. He's going to talk about that. And there's something called a Brent type theorem, named after the great early computer scientist, Australian computer scientist, Richard Brent. A Brent type theorem which lets us connect the abstract idea of parallelism to what happens when you implement it with certain resource bounds, like only P processors, or only P processors with thus and such cache behavior, cache configuration. You can then make predictions about its runtime on a concrete thing, but you completely separate out, okay, the abstract idea of parallelism from its concrete realization, meaning the design of a scheduler. So the proof of the Brent type theorem is a constructed proof that gives you the scheduler that tells you how to achieve a certain complexity bound. Oh, it's gorgeous. So this idea is originally, go back to Guy Blalock, my colleague at CMU. I love these ideas, as you can tell. They're extremely beautiful. This is a way of formulating it that makes it mesh in with this idea about using a modality for sequentializing things. It's just that the essence of parallelism is sequentiality from here to here. The rest can do whatever it wants. That's the critical idea. And so, so this is what we do, and we do all this in call by value or in a by value interpretation of variables. It falls out. That's how it falls out. It can't be done by name. You're screwed. Okay. So it's a historic error, in my opinion. It's like dead end. That's never going anywhere. Okay. And this is the reason. These are the reasons. These are part of the reasons. Okay. So I think, I don't know what my time is, but I think that's kind of enough for me today that I want to say. So I'll take further questions, and then I continue tomorrow. So that's what'll happen.